Current, electricity. In this chapter, first we go through Ohm's law. Electric current. Electric current is constituted by the flow of electrons in a conductor. Electric current is constituted by the flow of electrons in a conductor. Consider the conductor AB. The end A of this conductor is connected to the positive of the battery and the end B is connected to the negative of the battery. Across the terminals of the battery, a potential difference is maintained by chemical reaction. This cell creates a potential difference across the ends of the conductor A and B. The end A will be positively charged and the end will be negatively charged. So A becomes a higher potential end and B becomes a lower potential end. There will be excess of electrons at the end B and positive charge will be created. Electrons will be removed from end A and thereby charges will be created and an electric field is created inside this conductor from A to B. An electric field is created from A to B. In this electric field, the electrons will flow opposite. Electric current. Electric current is constituted by the flow of electrons in a conductor. Electric current is constituted by the flow of electrons in a conductor. Consider the conductor AB. The end A of this conductor is connected to the positive of the battery and the end B is connected to the negative of the battery. Across the terminals of the battery, a potential difference is maintained by chemical reaction. This cell electric current is defined as the rate of flow of charge across the conductor. The rate of flow of charge through the cross section of a conductor is defined as the current. Across the cross section, if the charge Q flows in t seconds, then the current I is equal to Q by T. Current I is equal to Q by T. Q is the amount of charge that crosses any cross section of the conductor in time t. If 1 coulomb of charge passes in 1 second, then we say the current is 1 ampere. The unit of current is ampere and it is equal to 1 coulomb of charge, flow of 1 coulomb of charge across the cross section in 1 second. This charge is constituted by 6.25 into 10 to the power of 18 electrons. So in 1 second, 6.25 into 10 to the power of 18 seconds will cross the cross section. Then 1 ampere of current will be established in the conductor. In a conductor, it is the flow of electrons that creates current. But in electrolytic solutions, it is the ions, positive and negative ions, they constitute the current inside the electrolyte. And in a semiconductor, there will be both flow of holes and electrons. Flow of electrons and flow of holes takes place and both of them will constitute the current. Ohm's law. Ohm's law. It is stated as at constant temperature, the strength of the current in a conductor is directly proportional to the potential difference across it. The current in a conductor is directly proportional to the potential difference across its ends, provided the temperature of the conductor is constant. So if I is the current flowing when the potential difference is V at constant temperature, then I will be proportional to V. As V increases, I also increases. But the ratio V by I is a constant. That constant is termed as the resistance of the conductor. So Ohm's law is mathematically written as V is equal to IR. R is the resistance of the conductor. Its units are ohm. Ohm is its unit. R depends on the material of the conductor, the length of the conductor, the cross section of the conductor, and the temperature of the conductor. The resistance of a conductor depends on its material, its length, area of cross section, and temperature. The resistance of a conductor is directly proportional to the length. If length increases, resistance increases. And it is inversely proportional to the area of cross section. So R is proportional to length L and R is inversely proportional to area of cross section A. So R is proportional to L and R is proportional to 1 by A. A device which has got resistance is called a resistor. Sometimes we represent fixed resistance by the above figure and variable resistance by the figure below. The resistance may increase or decrease with temperature. With temperature, sometimes the resistance increases and sometimes the resistance decreases. Also with PD, sometimes by applying increasing PD, the resistance may increase or decrease in certain devices. When we consider in a diode, in a diode current flow takes place. The resistance of the diode depends on the direction of current flow. The resistance of a semiconductor diode depends on the direction of current flow. In one direction it will have less resistance, in the opposite direction it will have high resistance. We can use the relation V by I always to find the resistance, whether the resistance is constant or a variable. We can always use the relation V by I to find the resistance. If V by I is constant, then such a device is called ohmic resistor. If the ratio V by I is a constant, it is called ohmic resistor. If V by I is not constant, then it is called non-ohmic resistor. It is called non-ohmic resistor. The temperature dependence of resistance is given by the relation. The temperature dependence of resistance is given by the relation RT is equal to R0 into 1 plus alpha T. RT is equal to R0 into 1 plus alpha T, where RT is the resistance at T degree centigrade, R0 is the resistance at 0 degree centigrade, and alpha is known as temperature coefficient of resistance. Alpha is known as temperature coefficient of resistance. Ohmic and non-ohmic resistors. Ohmic and non-ohmic resistors. A resistor which obeys Ohm's law is called a ohmic resistor. That is, V by I is always constant. If we draw a graph between V and I, taking V on x-axis and I on y-axis, we get a straight line passing through the origin. So, if VI relation passes through the origin, such a resistor, and it is a straight line, such a resistor is known as ohmic resistor. In such a resistor, if the direction of the potential difference is interchanged, that is, if the connections of the battery are interchanged, positive terminal is connected to the second end and negative terminal is connected to the first end, then the same amount of current will flow in the opposite direction. The magnitude of current will not change, but the direction of current flow will change. Examples of such resistors are metallic resistors at constant temperature, metallic resistances at constant temperature, and copper sulfate solution with copper electrodes is also a ohmic resistor. Then, when the Ohm's law is not obeyed, if Ohm's law is not obeyed, then such resistors are known as non-ohmic resistors. Then the curve between I and V, between potential difference and current, is not a straight line. It is not a straight line, it is a non-linear. In the below graph, we are showing the variation, the increase of current with voltage, but it is not constant. The current increases more with the voltage. So this is one type of non-ohmic resistor. If we observe the curve between potential difference and current in a semiconductor diode. In the forward direction, when the voltage is increasing, the positive value of voltage is increasing, then the current will also increase. Though it is non-ohmic, the current increases. But when the direction of the current is reversed, if the polarity of the battery is interchanged, then in the reverse direction, a small current flows in the diode, that too in microamperes. In the forward direction, it flows in milliamperes, and in the backward direction, it flows in microamperes, very small current. So the magnitude of current changes, and a large resistance will offer in the reverse direction, backward direction. There is another device known as thermistor. In thermistor, if the applied voltage is increased, the current increases. Sometimes two currents will pass at the same voltage. For the same voltage, there will be two currents. So the graph is shown in the figure. Examples of non-ohmic resistors are semiconductor, thermistor, electrolyte, dilute sulfuric acid with tungsten electrodes, and neon gas bulb, etc. These are some of the non-ohmic resistors. Specific resistance or resistivity of a conductor. It is a physical property which depends on the substance of the conductor. We know that the resistance R of a conductor is directly proportional to its length and inversely proportional to its area of cross section. So R is proportional to length L and R is inversely proportional to area of cross section. Combining these two properties, we get the relation R is proportional to L by A. This proportionality is replaced with a constant rho. So we write R is equal to rho L by A. This proportionality constant rho is called as specific resistance or resistivity of the material. Specific resistance or resistivity of the material. When length is equal to 1 meter and area of cross section is equal to 1 square meter, then R is equal to rho. Using this relation, we can define specific resistance as the resistivity of the material of a conductor is equal to its resistance for a conductor of length 1 meter and area of cross section 1 square meter. The resistance of a conductor of 1 meter and area of cross section 1 square meter is a measure of its specific resistance or resistivity. The resistivity of a conductor depends on the temperature. It is measured with the unit ohm meter. Conductance and conductivity. Conductance and conductivity. Conductance, the reciprocal of resistance is called conductance. Conductance is defined as the reciprocal of resistance. It is not a property of the material. It depends on the dimensions of the substance. If a current I is established in a conductor due to a potential difference V across its ends, then its conductance is I by V. I by V is called its conductance. It is represented by G. So G is equal to I by V. By definition, G is equal to 1 by R. Conductance is the reciprocal of resistance. The unit of conductance is mho, M-H-O, or Siemens. Then let us define conductivity. It is defined as the reciprocal of resistivity. Reciprocal of specific resistance or resistivity is defined as conductivity. Conductivity is also a property of the material. The SI unit of conductivity is mho per meter or Siemens per meter. mho per meter or Siemens per meter. Both conductance and conductivity are temperature dependent. Both are dependent on temperature. Temperature coefficient of resistivity. Temperature coefficient of resistivity. It is defined as the fractional change in resistivity per unit rise in temperature. It is defined as the fractional change in resistivity per unit rise in temperature. For a small range of temperature, the increase in resistivity of metallic conductors over a small range of temperature, the increase in resistivity of metallic conductors is linear. That means the increase is constant. Over a small range, the increase is constant. The increase in resistivity with temperature is constant. If we represent the resistivities of a conductor as rho 0 and rho t at temperatures T0 and T, then the relation is rho t is equal to rho 0 into 1 plus alpha into T minus T0. Rho t is equal to rho 0 into 1 plus alpha into T minus T0, where the constant alpha is called temperature coefficient of resistivity. Alpha is called temperature coefficient of resistivity. The temperature T0 is taken 0 degrees centigrade or 20 degrees centigrade in general. In general, the value of T0 will be taken as 0 or 20 degrees centigrade. A graph is drawn between resistivity and temperature coefficient and temperature. For a small range of temperature, you notice that it is a straight line. That is, the increase is constant. We have derived the relation for resistivity, relation with temperature. From the above relation, we get alpha is equal to rho t minus rho 0 by rho 0 into T minus T0. From the above relation, we get alpha is equal to rho t minus rho 0 by rho 0 into T minus T0. Let us represent rho t minus rho 0 by rho 0 as d rho by rho, change in resistivity by resistivity, d rho by rho, and T minus T0 as dt, change in temperature. Then alpha is represented by d rho by rho divided by dt. D rho by rho is fractional change in resistivity and dt is change in temperature. So this is the relation that is used for defining alpha. D rho by rho has no units. Therefore, the unit of alpha is per degree centigrade or per degree Kelvin. Application of temperature dependence of resistivity. Application of temperature dependence of resistivity. Nichrome is an alloy of nickel, copper and chromium. Nichrome is an alloy of nickel, copper and chromium. It has got high resistivity. So it is widely used in heaters as an element. Nichrome is used as an element in heaters because of its high resistivity. It is an alloy of nickel, copper and chromium. There are another two alloys, manganese and constantan. Manganese is an alloy of copper, manganese and nickel. Manganese is an alloy of copper, manganese and nickel, and constantan is an alloy of copper and nickel. Constantan is an alloy of copper and nickel. These two substances have low resistivity. Because of their low resistivity, they are used in resistance boxes and also in potentiometers and meter bridges as resistance wires. The resistivity of these substances is almost constant over a small range of temperatures. For a small rise in temperature, the resistivity is almost constant. The resistivity of carbon decreases with rise in temperature. The resistivity of carbon decreases with rise in temperature. This property is used in controlling the current in a device. For controlling the current in a device, sometimes the decrease in resistance of the carbon with temperature is used. The property of decrease in resistivity with rise in temperature is used in controlling certain devices. Thermistor. Thermistor is a heat sensitive device. That means the resistance of thermistor varies with temperature. That's why it is called as heat sensitive device. It is a non-ohmic resistor. Generally, thermistors are made of semiconductor compounds as the oxides of nickel, iron, cobalt and copper, etc. They are made of semiconductor compounds as oxides of nickel, iron, cobalt, copper, etc. A thermistor is generally enclosed in a capsule with an epoxy surface. It is enclosed in a capsule with an epoxy surface. Thermistors have a very high alpha value. Their temperature coefficient is very high. That means the variation of resistance is very high with a small change in temperature. We use the following symbols shown at the right side, the middle, the symbols. These are the symbols that are used to represent thermistors. A resistance in a circle and a box which is crossed. They have both positive temperature coefficient and negative temperature coefficient. Thermistors of positive temperature coefficient are available and thermistors of negative temperature coefficient are also available. For certain thermistors, the resistance increases with temperature, so they will have positive coefficients. For some other thermistors, their resistance decreases with increase in temperature, so they have negative temperature coefficient. Thermistors are used in measuring very low temperatures of the order of 10 degrees Kelvin, 0.1 degrees Kelvin, very low temperatures. And the power of a microwave. The power carried by a microwave can be measured using thermistors. Thermistors are used to stop sudden surges of currents into sensitive devices. Thermistors of negative temperature coefficient are useful in stopping sudden rise of currents in certain devices. That is known as sudden surge of currents into certain devices. Electric current is constituted by the flow of electrons. The conventional current direction is opposite to that of electron flow direction. The flow of 6.25 into 10 to the power of 18 electrons in 1 second through the cross section of a conductor, it constitutes 1 ampere of current. The current in a conductor is directly proportional to the potential difference applied across its ends. This is known as Ohm's law. And this is constant at a constant temperature. V by I is equal to a constant at constant temperature, that is indicated with R, known as resistance. The resistance depends on the length of a conductor, its radius, its temperature and its material. It is measured in ohms. The reciprocal of this is termed as conductance and it is measured in Mohs or Siemens. A property that depends only on the temperature of a substance is known as resistivity. The reciprocal of this resistivity is called as conductivity. resistivity is measured in ohm meters and conductivity is measured in mhos per meter or Siemens per meter. Conductors that obey Ohm's law are termed as ohmic conductors, and those that do not obey Ohm's law are known as non-ohmic conductors. For ohmic conductors, the VI relation is a straight line passing through the origin. For non-ohmic conductors, it is not a straight line, but it is a curve. And there are electrolytes, thermistors, etc., which are non-ohmic conductors. Thermistors are heat sensitive devices. Their resistance changes drastically with temperature. We study the variation of the resistance or resistivity with temperature by means of a constant known as temperature coefficient. Thermistors have both positive temperature coefficient and negative temperature coefficient. That means a substance whose resistance increases with resistivity increases with temperature is called as having positive temperature coefficient. If the resistivity of a device decreases with increase in temperature, we say it has got negative temperature coefficient. We study this property, and this property is useful in identifying elements suited for different purposes. For example, if you want a heating device, highly heat producing device, it must have high temperature coefficient. If you want a device, a substance which has constant resistance, it must have very low temperature coefficient. Like this, we identify substances.